In this video, we're going to learn how to analyze this refrigeration or heat pump cycle within EngineeringPaper.xyz. This is using the thermodynamic properties which are provided by the CoolProp library. There's a separate introduction video to get you started if you're new to this type of thermodynamic property analysis. So let's dive into this analysis of this refrigeration cycle. We're going to make some simplified assumptions that are kind of standard in this first pass of analyzing a refrigeration cycle. First of all, we're going to assume the compressor is isentropic, meaning that the entropy is constant during the compression phase from 1 to 2 here. The condenser and evaporator, we're going to ignore any pressure drops that go across those components. So the pressure will be constant. This is the isobar line here, as you can see in this pressure versus enthalpy plot. In the condenser and evaporator, we'll assume constant pressure. And we're also going to assume that the expansion valve is isenthalpic process, so the enthalpy is constant as the fluid enters and leaves that expansion valve. So we just have a change in pressure and temperature, but no change in enthalpy across that valve. So that's an idealized assumption. So we have these four states we're going to analyze. One thing to note, we have the temperature versus entropy plot here and the pressure versus enthalpy plot. In both these plots, we have, these are phase diagrams, so we have this saturation line here. And what that means is below this line, we're in a saturated state. So on this left edge is on both plots, this is the saturated liquid state. And then on the right edge, it's a saturated vapor. In between, it's a mix between vapor and liquid. We look at this as quality when we evaluate these functions. So we have a quality of 0 when we have all liquid, a quality of 1 when we have all vapor. To the right of this plot, it's in a vapor phase. Same over here, and to the left, it's in the liquid phase. So this, whether we're in a saturation region, when we're in a saturation region to get our state, we always have to provide quality. And when we're outside the saturation range, then we can get our state from pressure and temperature. So our inputs to this, we need to know the condenser temperature and the evaporator temperature, which we'll enter. And also to get the total capacity, either cooling, the heat that enters the evaporator, if we're looking at a refrigeration cycle, or the heating, the heat leaving the condenser, if we're looking at a heat pump cycle. We need to look at that. And in order to evaluate that, we need the mass flow rate of the refrigerant as well. So let's start our engineering paper sheet. We have a blank sheet here. We'll just call this refrigeration cycle. And this also, or heat pump. All right, so first we're going to just do our inputs. So let's add a label, just indicating that we're going to put our inputs in here. We're going to have an input as our condenser temperature. This will be the higher of the two temperatures. We'll put this as 30 degrees C. We could put degrees F as well, just use the appropriate units. I'll be typing in units most of the time here, but we do have the units button down here that we can use to enter the units. So here in the temperature tab, we have the temperature choices. So we can do T evaporate. So the underscore character allows us to do a subscript. The arrow gets us our other subscript. Equals -20. And I could just do degrees C here. We also need to enter the mass flow rate. So I'll do N_DOT, right arrow, equals 0.3, we'll do 0.345 kilogram per second as our mass flow rate. We just put our units in our square brackets. All right, so now we do the outputs here. So I'll put a label, we'll say outputs. Let's do label for inputs and outputs, and do shift enter to add a new math cell. So our outputs, I'll just define the variables here. Right now they'll not have a value yet until we do our calculation. So we'll do a coefficient of performance for cooling equals, and right now these are just kind of placeholders. Coefficient of performance for heating. Tab also gets us up to the top level after a subscript. And we'll also do our total cooling capacity, Q underscore cool, tab equals, and then Q underscore heat, our total heat capacity. And then we also want our work that's going to require to run the compressor. All right, so let's do our calculations. So I'll add another label, call this calculations. All right, shift enter to add a new math cell. All right, so the first thing, we'll go back to our diagram here. We're given the temperatures, right? So we're given, let's look at our temperature versus entropy plot here. We're giving the temperature at our condenser at the bottom and our evaporator at the top here. And so 4 and 1 are going to be at our condenser temperature, and then our 3 is going to be at our compressor temperature. And then from that, So let's assign those first. So T1 and T4. So T underscore 1 equals temperature evap. And then comma, I can do a second assignment here. T4 is also a temperature evaporator. And then our T3 is going to equal our temperature condenser. So that's just using what is kind of given in the problem. All right. Now from that, we can get, because here we're at a saturated vapor, we'll get our pressure here at 1. And then this is a constant pressure line, as we can see here, constant pressure line here as well. So we got a saturated liquid here. So at T1, saturated vapor, so quality of 1, we'll get our pressure. At 1 and 4, to get our pressures at 2 and 3, we'll look at 0.3, T3, where we have a saturated liquid, quality of 0. So we need to define our functions in order to be able to do this. And so we have these fluid property functions. So we'll hit the fluid drop here to get our fluid property functions. We're going to use, for all these, now one thing we're going to use this sheet fluid button here. And we'll see why we're doing this, but we need to click that first. Then we'll choose our refrigerant. We'll choose our refrigerant as R134A. So several refrigerants we can choose from. R134A. Okay, so now we have refrigerant. We got to choose the output we want. So we know temperature, we're trying to get pressure. So we're going to get pressure. We need to tell what inputs we're going to use. We know temperature, and we know we're in a saturation range, either quality of 0 or 1, depending on what point we're looking at. So we're going to put our second input as quality. What this gives us is a function we can now call that gives us our pressure given a temperature and a quality. So we can hit the copy button here, and then I'm going to hit enter on this cell, Control V, and we just call this like a function. So we're going to say that P3 equals, and our P3 has a temperature of T3 and a quality of 0. So we're going to call it with temperature T_3, which we've already defined, comma, quality of 0. So we just say 0. And that gives us a pressure. And we'll do these in kPa as a more convenient pressure unit. So that gives us our P3. Now which is the same as P2, so we can say P, while we're at it, P2 equals P3. All right. And now we have P4 and P1. So here we know the temperature and the quality. Here, the problem at 0.4 is we don't know the quality. It's somewhere between 0 and 1. But at 0.1, we do know the quality. We know the quality is 1. And so we'll use T1. So we use that same function. So we'll say P4 equals that same function. It should still be in the clipboard, Control V. And now it's T1, comma, quality of 1, since it's a saturated vapor, 100% vapor. And then again, we'll do equals kPa to give us our pressure. And we also know that in addition to P4, it's also, sorry, that's P1, but P4 is the same thing. So technically it's P1, but P4 is also equal to P1. So that was still correct. All right, so we have our 4 pressures. And again, because we know we have constant pressure in the condenser and evaporator as our assumption. The one temperature we still don't have is this T2. We know the temperature, we know the pressure at 0.2, we don't know anything else. So we need 2 things in order to determine the temperature. The one thing we know is that the pump, we're assuming, is an isentropic process, so the entropy at 0.1 and 0.2 will be the same. We do know the pressure and temperature at 0.1, but we also know the quality is 1 at 0.1. So from that, since we're in a saturation region, we need to use quality. We can get the entropy at 0.1. We'll call that entropy S. So S_1 equals, so we need to define a function for this. So each of these functions, we make a new fluid cell. We can put these on the bottom of the page like I'm doing here. So now that I've selected a sheet fluid, I can click the sheet fluid icon and it'll now automatically switch to that fluid I've already chosen. The benefit here is if I switch it in one cell, it switches in them all, so I can evaluate different refrigerants. We want a temperature, actually we want entropy out to get entropy at 0.1. We know temperature or pressure. Let's do temperature as our input. And we know it's in a saturation region, so we need to provide the quality. We'll copy this. So our S1 equals our entropy given temperature, T1, and we're at saturated vapor again. So that gives us our entropy at 0.1. This is in kilojoules per kilogram times Kelvin. Now we also will eventually need our enthalpy here as well. But before I get that, we know that the entropy at 2 is the same because of the isentropic pumping process. So let's just say that S2 equals S1. And while we're evaluating 0.1, let's get our H1 here, which is our enthalpy, because we'll need that when we calculate the heat in and heat out in the work in. So we need to define a new function again. We can't change these existing ones because that'll mess up our functions, so we just need to keep adding as the functions with different inputs and different outputs. Again, we use sheet fluid to automatically switch to our sheet fluid. We're going to do enthalpy as an output here. Again, the input is temperature and quality. And we'll copy that. Go back up to here and do that as T_1, comma, quality of 1. And this is going to be in kilojoules per kilogram as our units for enthalpy. So now we can get T2 because we know we're out here kind of out of the saturated state. So now we know our entropy and our pressure at P2. So now we can get our temperature at state 2. So we got T_2, and we need this as a function of pressure and entropy. So let's make a new function for that, since it's a different set of inputs and outputs. Again, use our sheet fluid first, do that selection first. We'll do temperatures and output. Obviously, we can't have temperatures and input. It tells us that we're going to have pressure as our first input. We know the entropy, so we'll have that as the second input. All right, so then we have T2. I'll Control V to paste that. Is P2, and I know the order here because it gives me in the name, P2 comma S2. And that gives me a temperature. It's going to be in Kelvin by default, but I can do degrees C if I prefer. So at each point, we're going to need the enthalpy as well. We need enthalpy at all 4 points, pressure and temperature at all 4 points. So we still need enthalpy at point 2. Let's create a new function which gives us enthalpy in terms of temperature and pressure. Because we know that at point 2. We could also do it in terms of entropy if you wanted, but we'll just do in temperature pressure because we will be able to reuse that function. So use sheet fluid, we'll do enthalpy, we'll do temperature and pressure, that's the default. Copy that. And so we'll have H2 now equals H given TP, that's going to be T2 and P2 at state 2. And that gives us, again, we'll do kilojoules per kilogram for enthalpy. Now all we have left, we have temperature and pressure everywhere now. We have enthalpy at points 1 and 2. We just need enthalpy at points 3 and 4, and really only need one of those because they're same enthalpy. We're using an isenthalpic expansion valve here. So at point 3, we're again at a saturation stage with quality of 0. So we'll use that. We know the temperature. We already have that function defined. So we'll say H3. We've used this function before, but now the saturation or the quality will be 0. So H, I can type it in instead of pasting it as well. So T3 now and quality of 0 since we're a saturated liquid. And we'll do this in kilojoules per kilogram. And that gives us 241 for the enthalpy at point 3. And then we'll do the same thing. H4 is its same enthalpy. Now we have everything we need in order to calculate the amount of cooling, amount of heating, and the amount of work to go in, and also our coefficients of performance. So let's look at cooling first. So cooling is happening at the evaporator between 4 and 1. And so if we take the enthalpy at 1 minus enthalpy at 4, we'll just look at all of them as positive. So we'll take high enthalpy minus low. So H1 minus H4 times the mass flow rate, that'll give us the total cooling, mass flow rate of the coolant, which we've already defined as m dot at the top. And so we're trying to get this Q cool. So let's do our calculations here. So Q cool equals, again looking at this, H1 minus H4 times m dot. So m underscore dot tab, times, I always have to put the multiplication symbol. You can't, all multiplication symbols have to be included. There's no implied multiplication. And so H4 tab minus H1. And this should be in kilowatts. We'll put it in kilowatts. Now that's negative. Let me swap that around and do 1 minus 4 here, just to keep it positive. And let's put it in kilowatts. So I can do it in all sorts of units. So I can re-output it here. And I can go to my power tab on the units. I can do everything from boiler horsepower to tons of cooling if I wanted to. So it's about 14 tons of cooling. So we have all kind of these crazy HVAC units available if you would like. Let's do our Q. Let's do our work in so we can do a coefficient of performance. So we'll do work compressor. Again, we're going to have m dot on the outside. And we just need to just figure out what H is. So the compressor is operating between 2 and 1. So H2 minus H1. And that'll be in kilowatts. So this is a 12.6 kilowatts of input. So then by definition, a coefficient of performance of cooling is how much useful cooling we're getting out of the system. So Q, cool, divided by, whoops, gotta hit the right arrow, divided by our work of our compressor, and then right arrow twice, and we get 3.96. And so we're moving more heat than the amount of work we're putting in, which is typical for just sort of refrigeration cycle, and it's the benefit of these cycles. Now, this is a theoretical limit, right? Because we're not including some of the losses in the compressor would be the most significant loss that we're not accounting for. Okay, now let's look at this in terms of heat pump. If we're desiring to get the heat out, trying to heat our space, then we worry about Q heat, which is going to be our H2 minus H3. So let's calculate that. So Q heat equals m dot times H2 minus H3. Put that into kilowatts. So there we have 62 kilowatts of heating. Now again, we can do a coefficient of performance for heating. Oops, shift tab back. Heating equals, that's going to be our useful heat out, Q underscore heat, tab, divided by our work compressor, and that equals 4.96. So theoretically, the coefficient of performance for heating is always going to be 1 greater than coefficient of performance for cooling. You can see that from this diagram, because for this idealized isentropic process, all of the compressor work goes into this from H1 to H2. So that compressor work gets added into the heat output. So that adds 1 to our coefficient of performance for the heating in the cycle. So that gives us our kind of our limit for the coefficient of performance for heating as well. One thing to note, the m dot doesn't affect. So now if we go back up to our outputs, we have all our outputs here. If we didn't want to change all these outputs individually, we can also change our default units. So if I go to SI, let's choose our default power. Find power here. There it is. Do it kilowatts, and we'll do a default pressure. All right. So it'll give us, and then we have too many significant digits here. So I'm going to change this to like 4, make it more reasonable. All right, so all of our outputs have updated since we've used those units. One thing to note, since the m dot will cancel out for the coefficient of performance, it only affects the capacity as far as Q heat and cool. So I can adjust that, and the coefficient of performance will remain the same. But I see the difference in the heat and cooling capacity and the amount of power required of the compressor. All right, I'll post a completed, more annotated version of this worksheet into the notes. Otherwise, you now know how to analyze a refrigeration cycle in EngineeringPaper.xyz.